Curtis?
Hello.
Still that doesn't work, huh? You want to try that?
Get up the volume on the TV.
Yeah.
Oh, yeah, I can.
This I'm sure. I think I tried. I think it's
These buttons usually work for you.
I don't use any of this because I use other remote, right, for the camera.
Okay. I'm not sure.
So
I'm
you
trying to move around, but it's not letting me.
see. Curtis, can you say something?
Hello.
Yeah, okay. You still don't. Okay. The last time you could fix it, right? I thought maybe it was just HDMI. Right. Yeah. Okay. I did grade the exams. So I updated the grades about half an hour back also for you guys noticed. So the curve this time was 20% of, that's 20% of what you lost is returned. Remember, curve is t plus y times a times 100 minus t. So you multiply this as 0.0. And y is your extra credit. And this is done for the total, right? And before, so for this, so it was 95, 95, 80, 76, 65, and 36. So this is before the curve. After the curve, this becomes 96, 95, 82, 86. Right, so that's your final grade, and that's A, that's B, and so on. I haven't posted this yet, but we will have a homework 12 to November 20, Friday. And there'll be one more homework due after that on 27. Not 27th, right? So this will be December 4th. And final exam. What's the day on December 11th?
Should be
Before, yeah, Friday, right? So due. It is 2:45 to 4:45, but this is going to be a take home. Right, so that's not relevant. Let's take home. Let's do it. And there are no, we are not, are you guys allowed to come to the campus after Thanksgiving?
I think they allow it now if you have a good reason to come back, but no. you
Yes,
can
so
stay home.
as far as I know, I don't know whether you can come to the campus or not, so I don't think you can be in the class. So you have to be on. But I assume that I can come and teach here. But you guys cannot be there, so that's clear. So you guys have to attend it using online. Most probably I'll be teaching it here. So as far as I know, I think it's still comparable. Refer to that and check that I can actually do that. So we should be able to go as we usually go. Okay, so until now we have been confining ourselves to electrostatics. We want to move out and keep the whole set of Maxwell's equation, and at least before the end semester ends, at least to do few simple things there. And then when we come back, we will do magnetostatics and the full electrodynamics in its full form after a month or so in the next semester. So let's see Maxwell's equation. Maxwell's equations. We have del dot with epsilon naught E. Let's have no materials around. So let's say this is R comma T now. That's equal to okay. Right. And we have the divergence of the magnetic field similarly. It should be the magnetic charge density, but we don't have magnetic charges. That's 0. But no magnetic charges means that's the curl of the electric field is exactly equal to negative of the time derivative of the magnetic field. That's your Faraday's law in your undergraduate introductory physics. You should have seen this. When you change the magnetic field, you bring in a magnet close to a wire, and it induces a charge. This is how electricity is produced. Waterfalls, they turn the turbines, and if you keep a magnetic field around, you actually can generate electric field, which is the voltage is generated. And finally, we have the cross. Let's write it as B or mu. Let's write it as del cross H. Is equal to time derivative with respect to D RT plus. Okay, one more. Let's switch. Oh, for completeness, I should also say D is equal. So E is equal to epsilon naught times electric field, and B is equal to mu naught times H. Let's see how the electric potentials come about. Remember, in electrostatics, what we do is that the cross of something is equal to 0 tells you that electric field has a negative gradient of pi. But that's no more true. We are stuck here. So let's see how we can proceed. This surely, the second equation, so tell that with D is equal to 0 instead, always implies that since curl of a divergence of a curl is 0, so this implies that B actually is equal to del cross A. Or another way of saying it is that if I define my magnetic field to be a curl of a vector field, it is guaranteed that this will be equal to 0. Because divergence of a curl is always 0 because of the antisymmetric properties of the vector gradient, if you want. So this implies that del dotted with del cross A is always 0. Right? That's because this curl involves a Levi-Civita symbol or an antisymmetric properties involved here. And then you're taking the divergence. This is a symmetric operator. The curl is an antisymmetric operator. They don't get along together. Okay, is that clear what I mean? So there's an antisymmetry and symmetry coming in. So that makes sure that that's equal to 0. So this definition always guarantees that. So D is equal to del cross A. And in that way, since earlier we said electric field is gradient of electric potential, this is defined to be the magnetic vector potential. Okay. And that's always true. So now we are talking about the full Maxwell's equation. This is in general true, whether it is statics or not. We are not doing statics, always that is true. So, and until now, we haven't discussed this probably even in the introductory physics course because we don't use it much in the laboratory. So it's the electric potential that you work with. Or is that a magnetic vector potential? Have you guys used it? Do you do any electrical engineering? Are you in the electrical engineering department or?
No, I'm interested in it. I watch a lot like videos and stuff.
Yeah, but do you? Yeah, there's no magnetic vector
I don't
potential.
think that you can measure. Not that I-
Yeah, that's correct. Can you measure it even? But then even electric potential in principle, that's harder to measure. It's only the change in scalar potential you can measure. So yeah, that's a good point. So you cannot even measure it. So there are issues with that, and we'll talk about it a little. Good point. Yeah, so we don't come across this level. So why not, right? So that raises the question, why not? So let's talk about that a little. But before that, let's introduce what is electric potential. If this is there, if this is 0, then we know what is electric potential. So what does it mean? So what is electric field now? So let's, starting from here, this is always true. Let's put this back in here, right? So the third equation. So use this in the third equation. So using, we call this equation numbers, right? 1, 2, 3, 4. So using del cross A in 3. Okay, so now we have del crossed with the electric field. And let me write this onto the left hand side. So that's time derivative of del crossed with A is equal to 0. That's a true statement. Rewrite this in the form del crossed with electric field plus time derivative of the vector potential is equal to 0. Notice that to do this, I have interchanged the spatial gradient and the time derivative, right? Which is okay. Like this, we work with functions that commute under that operation, so that's perfectly fine. So it is, now we learned that earlier it was the curl of the electric field that was equal to 0. Now we realize that it is not the curl of electric field that is 0, it is the electric field plus this quantity that is 0. Curl of anything equal to 0 implies that this time it is not the electric field, it is electric field plus the time derivative of the vector potential. That is equal to the gradient of something. We usually choose this to be the negative gradient of something, that's just a notation. So we call it the vector or the scalar potential. So this is that's also magnetic vector potential. This is the electric scalar potential. Right. Clear? So we see the correction now that electric field is equal to negative gradient of potential. Yes, that's correct, but there is an additional term now. And these are all dependent on position and time. Magnetic field is still and these are called gauge fields. So phi for the potentials, phi and A are called gauge fields. And this, yeah, and we will say why they are called gauge. We will define what is called a gauge transformation. Okay, so that's good. So what is this? So why not write everything in terms of phi, right? Yes, question?
Electric equation, is that minus after?
Yes, this is minus. What I did was I moved this to the right hand side, correct? So that's a minus. That is one nice thing one can observe in this is that if I were to actually change my phi, so let's see the following. I start with a phi and I switch to phi prime with all the time and space dependence. So phi prime is equal to my old phi. So here I'm redefining my phi, and let me say it's plus the time derivative. This is going to be any arbitrary function of space and time. That's a huge statement. You give me any function, any arbitrary lambda, take the time derivative of that, and add to this scalar potential. So I start with the scalar potential and then I add anything I want pretty much, but it's time derivative. But if I do that and simultaneously, that's the only constraint, that simultaneously I change my vector potential also. Okay. I change my vector potential also in the following manner. So this is now plus gradient of that same field or of t. And let's see what happens. So this is called a gauge transformation. So above are called gauge transformation. And let's see what happens to the electric and magnetic field. Let's not even go to the Maxwell's equation. Let's see how the electric and magnetic field change under this transformation. And we notice that, so we have a magnetic field. Let's begin with the magnetic field prime of G, that's equal to the curl of the new vector potential, correct? Which is equal to L crossed with the old vector potential A plus the gradient of lambda, right? This shouldn't be confused with A, that's here, lambda. And that's equal to del cross A. And the change in this, so this is your old magnetic field, correct? Is equal to del crossed with del of lambda. That's your old magnetic field, B of RT if you want. What is the curl of two gradient operators? Curl of two gradient operators? What will it be? Yeah, probably 0. Correct. And why is that?
I'm trying to think of it.
So for a change, so I usually give an argument to that. So let's do this. So we have del cross del, right, acting on any function. Okay. This is a vector to begin with. So let's say that's vector V. It has an I component. So its ith component is equal to epsilon I j k gradient j gradient k. Right, that's your using your Levi-Civita symbol that we have introduced sometime back. Now, when I say that this should be equal to 0, the way it works is that this is antisymmetric in j and k. If I switch j and k, that is -1, but if I switch j and k in the derivative operators, it doesn't switch sign. So that's the way one argues it. But let's prove this in an algebraic way. So let's say this is the same as half of, so epsilon I j k f, that's the same, but then I want to show that antisymmetry. So I say this is the same as I j k, and I swap my k and j's, right? So this is k and j. What I've done here is that d by dx times d by dy is the same as d by dy times d by dx. It doesn't matter which one I act first. So that's the property I have used in here. Since it's the same, that is the symmetry as a factor of half, right? Exactly the same. Is that clear what I did there? So now somehow I have to show that this is actually the negative of this. So I've used the symmetry property. Now I use the antisymmetry property. So I'll keep this as it is. So that's 1 by 2 times epsilon I j k plus f. And I do know that if I switch my j and k here, I get a minus sign. That's epsilon I k j, okay, j. Right, that's perfectly fine. So what I did is in the first step, I swapped this j and k, that's symmetry, so that's plus sign. In the second step, I swapped by Lewis-Levitas symbol, but that's antisymmetric, so that's just sign that gives you a minus. Now, why should these two be the same? Notice these are summations, right? J and k are dummy. So I can use anything I want. So I can replace all my k's with j's. But then I shouldn't use the j's anymore. So I replace all the j's with k's. Okay. Because they're dummy, right? Who cares what I call them? Like, because the summation of I is equal to 1 to 3 of xi is the same as summation over j to 1, j1 equal to 3 of xj. Right? These are dummy, like who cares what I call them? I can call them I, j, k, whatever it is. This one is x1, x2, x3, and same thing, x1, x1 plus x2, x2 plus x3. So same thing here. So I replace my k's with j's and j's with k's. So, and then I rewrite them. Epsilon I j k j k f, and this is minus of I j k j k. And now it's very clear that these two are exactly the same. So that's it. That's equal to 0. Right? So this is 0. What will this be? So extra credit, yeah, extra credit. So what about again two derivative operators coming together? Remember, derivative operators when acting sequentially, they commute, but here they first act on F and then act on G. So what is this equal to? Well, is this equal to 0? This is a question mark. So is this equal to 0? So that's so check it out. Okay. So that's equal to 0. So that's perfect. Right? So the magnetic field doesn't change. So if magnetic field doesn't change, this equation doesn't change, and at least this term doesn't change, right? These two terms do not change. Now let's see how the scalar potential changes. That's no electric field, right? So no scalar potential, electric field changes. So that's minus of gradient of phi prime minus d by time derivative of the vector of potential. That's equal to negative gradient of phi prime. We said is phi plus time derivative of this arbitrary gauge that we added, and minus the time derivative of A was the old vector potential plus the gradient of this arbitrary field. And we again see that this is negative gradient of phi minus A by dt. It's equal to minus what is something off here? Let's see. Gradient of time derivative of lambda minus of time derivative of gradient of lambda. Okay, that doesn't cancel, right? But then I have a choice. Right? So I obviously did not write this correct. So if I make this as my gauge transformation, this doesn't seem to cancel. But I only use the first one for showing this one. So I can change this to minus. So I can make this minus here. If this is minus, I change this down here. That's minus, that's plus. Right. And oops, that's not what I meant. This I wanted to keep same, so this is plus. Right? And now this cancels because again time derivative and spatial gradients cancel out, and this is cancel out, and that's your electric field, old electric field. Since this does not change your electric and magnetic field, these are called the gauge transformation. So, and this also means that phi and a are not unique. Correct? Give me any phi and a, I can always add or subtract this time derivative of these quantities, and they will get shifted. And that would mean that experimentally, it is not a good thing to measure, and that's what Christian was pointing out right in the beginning, that magnetic vector potential cannot be measured. Right? And scalar potential can be measured in the sense it's a change. Like we always fix one of them to be 0 on the ground, and that can be measured. So let's see, at least try to measure some or have some vector potentials and see what is this change, right? Instead of making it very general, let's make it very specific. For example, I can begin by asking if I have an electric field to be constant. So that's it. This is uniform. Uniform in position and time, in R and T. That means it's constant in R and T. It's just a constant number. Then what is phi for this? What is phi? What is A? I can surely choose like A to be 0, right? Because that we don't need that. But what is your phi, which will give you your electric field?
It just has to be dependent on the radius once, right? The derivative of potential would be, so not constant. By uniform, you don't mean constant.
Constant. By uniform, everywhere it has to be the same.
Okay.
It's really constant all through space, even in direction. So what is your phi in a very general sense? That'll give me my electric. So I should be able to operate this gradient on it, and it should give me an electric field. So the question is, I want, so what is phi, which when acted upon this should give me a constant, just a constant. So this is equal to constant
It would just be
in R and T. Yes.
proportional to the vector R, right?
Yeah, proportional to vector R. So you're saying phi is R, but that's a vector, scalar. Phi is a scalar, right?
So just the magnitude of R.
So you want a magnitude?
No, that would be one of
Magnitude of R.
magnitude of R is R hat over.
Yes, so this is equal to R hat. Right? You need electric field.
So electric field is Q over 4 pi epsilon not R hat.
But that's not point charge. We want a constant. Don't confuse. You just want a constant. Just like
Can phi be any constant then?
in principle, yes, but then it will go to zero, right?
Yeah. But
You want an electric field to come out of it. How will you get that out? So this is equal to R, yes. It's a vector. Right? And there's a negative, that's a positive, so I want to cancel that. I want a negative there, right? But that's a vector. I dotted, right? But I need an electric field on the right hand side. So why not put it dotted with this? Right? So let's try that. So negative gradient of phi, how does this work? So negative and a negative goes away. So I'm left out with gradient of R dotted with E. Notice this is supposed to act on this and this, but that's a constant. So this acts only on this. And that's equal to 1. And that's equal to 2. That's important in the sense most of the time in quantum mechanics, you work with electric potentials. Like you don't work with electric field. So you should know which potential to put in. So in the Schrodinger equation, you should know which potential to put in. So that if you want an electric field, hydrogen atom in an electric field, that's the potential you would put in. Okay, so now we know how to generate an electric potential for a constant electric field. But what I was wanting to do is, what about B? Right? So now next question is, I have B is equal to uniform in R and T. Okay. And the question is, what should my A be? So what should A be so that del cross A is actually equal to B, which is constant, right? So this is constant in R and T. Okay, so it's the same question you're asking. Very similar. Again, I should point out that these are all, this is a scalar potential, correct? So in principle, I can move this. This is not a unique solution. If this is a solution, there are many other solutions. Okay, so we'll explore that in the homework. That's a constant is an immediate solution, but we will, at least in this case, we will see a lot more possibilities. So let's, first of all, let's begin with what is A, right? It's not very obvious. It's very, even here, it is not immediately also obvious that this is, but with a little experience, you know that this is what is going to come out. And A for this matter, again, it's not unique. Remember, it's a gauge dependent quantity. A nice solution for this is B is a constant, and E is a constant here, right? Similarly, say this is B crossed with R. But why should that be true? Let's check that out.
A has to be perpendicular to B. Right? So no matter what
That's correct, but still that's not very obvious. Let's see this, okay? It's not very, like especially the factor of 2, y1 by 2 and all that. So let's see, this is usually tricky. Like this uses all this identities in here. But yeah, it has to be perpendicular, that's correct. So just as a proof, let me do this. So this is del cross A. So that's equal to 1 by 2 times del crossed with B crossed with R. And what is that equal to? You can use the back cab rule, just we have to make sure that derivative acts on R and it doesn't act on B. So this always acts on R. So it's a triple vector product. So first one is B, right? And this to this, right? So B and del dotted with R. Right? Back cab, right? And minus of cab. So now R is a vector, but it has to be getting operated with B. So this is B dotted with del times R. So this is the tricky part. That is, R is a free vector, but the derivative has to act on it. You cannot avoid it. It's easy to forget that. And so that's a tricky piece there. But this is 3. So if you ignore that, you get a 3 by 2. You get a 3 by 2 times B, which is not correct. But if you take care of this, this is equal to 1. And you get subtracted by the B, which is exactly what is, what happened? Some mistake, right? Because there was a factor of half. Which is exactly B. That's what. So this non-trivial way of representing the vector potential gives you your magnetic field. Let's see some simpler solutions like this. This is a nice, elegant solution, but let's see some simpler. As I said, this is not unique, right? So can you get other A and B's, right? So B is del cross A, correct? So in a very naive, simple manner, this is I, J, and K, and this is d by dx, d by dy, and d by dz. And A, I have a choice to choose, right? This is the determinant of this. I want this to be a constant. What should I choose by AX, AY, AZ here so that this comes out? Let us say this is constant times Z hat. So this is Z hat, by the way. Okay. So what should I choose here so that this comes out to be B? No vector, constant. What should this be? I have 3 components, I can choose whatever I want, but on the left-hand side, when I operate this, I should get a B in the Z hat.
EX.
Right, so I need a BX here, so that's what I heard, right? And I can choose 0. Correct? So notice this is 0, right? This is 0. This is 0, but derivative of Z is 0. Right? That's also 0, right? So that's equal to I hat d by dy of 0 minus d by dz of B times X. That's equal to 0 because derivative of Z with respect to X is 0. Minus J hat, that's again 0. That's 0, 0. So that's 0, 0. And finally, plus K hat, which is time derivative of X, sorry, derivative of X minus 0. So all this goes to 0, and it's only K hat times B that survives, which is correct. So vector potential A could be 0I plus Bx times J plus 0 times K. That's a solution. But clearly, that's not the unique solution. I can now change this to something else, correct? So what if I have minus by here? That will also do the job. This will also do the job. And that's a straightforward ones you can get. That's also a solution because derivative of y will give me where b and rest everything goes to 0. A linear combination of this will also work, right? If I have half of this and half of this, that will also work. So there are plenty of solutions just by looking at that, you can see. In fact, I can change this to a lot of other quantities here as far as x and y do not contribute, and that will also work. And that shows you the gauge dependence that you have. And this is a generic, nice function you can construct. So the take-home message here just is that if electric field is uniform, right, then phi is equal to minus r dot with E. If magnetic field is uniform, then A is equal to half B cross R. And there will be some I'll construct some very simple examples here. That will be your homework. And this time the homework will be small. That's what I'm planning to do. Okay. That's all. Thank you.